here we go. Okay, so here's the problem we're going to work through. It's quite similar to the constraint multivariate optimization example 4, which you can find linked in the lesson, but it's a slight variation to that. Okay, and I always told you that the Lagrangian method, while we are mainly looking at a bivariate problem with one constraint, can be extended to more than 2 variables and to more constraints. And the extension we look at today is that we are looking at 2 constraints. So, but step by step. Here we have a function. We have 2 arguments, x1 and x2, and here's our function, log x1 plus log x2. As we're having logs here, we already know that we are working on a quite restrictive domain. Okay, x1 and x2 have to be larger than 0, otherwise these log terms are not defined. And here are our constraints. So here's a constraint. This is one constraint, 2x1 plus 3x2 has to be smaller than 6. And we're having a second constraint. x2 has to be smaller, equal to 1 minus 1/6 of x1. So to understand what we're going to do here, it is best to start out by illustrating what these constraints mean. So we already know our coordinate system we're working in is really only where x1 and x2 are positive. Right? So our function lives in this space. And now the question is, what do these constraints imply? Both of them are linear constraints. So let's reformulate that first constraint in a form where we can immediately see what the linear constraint looks like. And we do that by bringing the x2 term on one side. Okay, and that means the other term. So we bring the 2x1, we subtract both sides of the inequality by, or we subtract 2x1 from both sides. So we are getting 3x2 is smaller or equal to 6 minus 2x1. And then we divide by 3. So basically what you get here is x2 is smaller or equal to 2, and then minus 2/3 x1. Okay, so that is that first linear constraint expressed in a form where we can sort of immediately see that, let's say here's 2. I want 2 to be, let's say here's 2. Okay, that we're having an intercept of 2 and then a negative slope of negative 2/3. So it's a bit flatter than 1. And you can see, when does it intercept the x1 axis? Well, when x1 is equal to 3, then we have 2 minus 2/3 times 3, so that's 2 and that's 0. So if 2 is here, okay, perhaps 3 is here. So this line will go like this. Okay, it's meant to be a line. Okay, so this is this yellow constraint. I'll make that yellow here. That is the yellow constraint here. But what about that second constraint? Let me just do this in red. That second constraint has an intercept of 1 and then minus 1/6 over x1. So where does that intercept the horizontal axis? Well, if x1 is equal to 6, then we have 1 minus 1, and that's 0. So where x1 is 6, so that's somewhere perhaps here, approximately. Okay, this is approximately 6. So that line goes somewhere like this. Okay, that is the red constraint. So, and in both cases, what we need is that the values, you can see here, x2 for that first constraint, the yellow constraint, x2 can be on that constraint or can be smaller than that constraint. So the values which are below, which are allowed, are the values on the line and below. Okay, so let me just do that in green. So basically, the first constraint restricts our values to this triangle. The second constraint restricts our values to the red triangle. So now you can perhaps immediately see that if our solution has to meet both of these constraints, the area of the function in which our solution can be is only this area here. Okay, this is the area where our solution could be, because that's the area where both the constraints are met. If you're in this area here, then the red constraint isn't met. If you're in this area here, then the yellow or green constraint here isn't met. Okay, so basically our problem is set up that we have to find the maximum of this function, log x1 plus log x2, but over that constraint area. Banali, are there any questions from the chat at this point? Because this is really important to understand what is set up here.
No questions yet.
No questions yet. Okay, so then let's see how we solve this with the Lagrangian approach. Okay, so we'll set up the Lagrangian function. And, sorry. Well, before I do that, we'll set up the constraints. Okay, so we know the constraints have to be formulated such that we have them larger or equal to 0. So let's look at that first constraint here. How do we formulate that so that we have that larger or equal to 0? Well, you see we have 6 is larger or equal to that on the left-hand side. So we bring the left-hand side over to the right-hand side. So it's 6 minus 2x1 minus 3x2 has to be larger or equal to 0. That's the yellow constraint. And we have a second constraint. So I have to give this a different name. So let's call it h, but you could call it whatever you want. And so how do we formulate that such that it is larger or equal to 0? Well, here we have on the larger or equal side, we already have 1 minus 1 over 6x1. We bring the x2, we bring that just over to the other side. So it's 1 minus 1 over 6x1 minus x2. Okay, so that is the red constraint. So now we're in a position to formulate our Lagrangian function. It will be in principle the same as what we've seen before, and the extension will hopefully be fairly straightforward to see. Now we're having two Lagrangian parameters, and I'll just call them lambda g and lambda h for the two constraints. So our function is log of x1 plus log of x2. So if we only had constraint g, it would look like lambda g times, so this is a subscript g, okay, times the constraint, which is 6 minus 2x1 minus 3x2. But now that we also have a second constraint, there will be just an additional term here, lambda subscript h, and now the h constraint, 1 minus 1 over 6 x1 minus x2. Okay, so it's the same sort of approach, our function, and then plus these two sort of penalty terms, one for each constraint. where each constraint has to be formulated in our standard way. Now, what are the necessary conditions? So the Lagrangian conditions. The partial derivative of the Lagrangian with respect to x1 has to be equal to 0. I'll add that in a moment. The partial derivative of the Lagrangian with respect to x2 has to be equal to 0. We'll just formulate that in a moment. Our constraints, basically it's just the restatement of the constraint. This has to be larger than 0. H, we have a second constraint, has to be larger or equal to 0. And now remember, we also had the complementary slackness condition, and we now have two of them. We have lambda g, so lambda subscript g times the constraint has to be equal to 0, and lambda subscript h times constraint h has to be equal to 0. Okay, so for every constraint, we added one constraint, that red constraint here. What we added was an additional constraint into our Lagrangian conditions and an additional complementary slackness condition. And now let's go back to our partial derivatives here. Let's just calculate these partial derivatives with respect to x1. So it's log of x1. We know the derivative of that is just 1 over x1. And we're having x1 here, minus 2x1 times lambda g. So it's basically minus 2 times lambda g. Then we are having an x1 here. So it's minus 1 over 6x1 times lambda h. So it's minus 1 over 6 times lambda h. And that needs to be equal to 0. Then our partial derivative of the Lagrangian with respect to x2, we have log, that should be ln, log of x2 is 1 over x2. And we have an x2 here, minus 3x2, so we have minus 3 times lambda g, minus 3 times lambda g. And here we have minus x2, so we have just minus lambda h, minus lambda h. That has to be equal to 0. So here are our Lagrangian conditions. So I hope that you see that in principle, nothing has changed through the addition of a second constraint. All we had to do was to treat that second constraint as we did our first constraint, and we had to add these two conditions, but they're not new, they're just the replications of the conditions for the first constraints. So any question at this point, Banali?
Again, not yet.
Okay, cool. All right, so that was just the setup. Let's see how we go through the solution. And now in the solution, I will, as I said before, you will get all the work stuff. I will try not to get bogged down in the algebra. I'll try to look at the bigger picture, because the algebra is all the same as it always is. I just try and look at the big picture to see what we are actually achieving with the algebra. So we have to find all the points, x1 and x2, and potentially also lambda g and lambda h, which meet these 6 conditions. We're having 6 conditions here, Lagrangian conditions. And we always did that in different steps. And the first steps we always followed was, let me use a new color, let me use nice purple, was that we tried to set the Lagrangian multipliers equal to 0 for a moment, pretending that there wasn't any constraint. So now in our case, we have 2 Lagrangian multipliers, lambda g and lambda h, and we are setting both of them equal to 0. That's the first step we're going to do. So remember, we're first pretending there are no constraints, see whether we can find an unconstrained maximum for our function. And then once we have one, if we get one, we'll just have to check whether at that point the constraint is met or not. So we're setting the lambdas equal to 0. That means we are left with, from the first condition here, 1 over x1 is equal to 0. And from the second condition, we're left with 1 over x2 is equal to 0. Now, of course, you can immediately see this doesn't work. Okay, we can't have, there is no value x1 and x2, which makes 1 over x1 and x2 equal to 0. Recall, even if x1 is 0, 1 over 0 isn't defined. And remember that x1 and x2 had to be positive. So we immediately know from here there is no solution, no unconstrained solution. Okay. What do we do next? Let me actually just wipe this away. Okay, this is exactly as also in the constraint optimization problem, multivariate optimization problem 4. I just want to use this space. Okay, there's no solution here. We have to find the solution somewhere on the constraint. So this is now where we see, hopefully, how the Lagrangian works. If we only had that yellow constraint or the green line here, what we would do next is that we would actually look for potential solutions on this line, right? Okay. If we only had the red constraint, what we would do next is we would look for potential solutions on this constraint. Okay, and we would, where's my pen? Looking here on that line, we would look for, that was our first constraint, that was the G constraint. We would look for solutions where lambda G is larger than 0. On the red line, we would look for solutions where lambda H is larger than 0. Okay. So what we're going to do is, well, basically first, we're going to look on the green line. And we will see whether we find a candidate solution. But then there's an additional step we need, because let's say we found this point here as a candidate solution. Well, this point isn't allowed by the red constraint. So we then have to do exactly as we did potentially do with our unconstrained optimum. If we find this point, we check whether it meets the constraint. In this case, it would not meet the red constraint. I should do that with red. Okay, it wouldn't meet the red constraint. And then we will look on the red line and we will find a potential solution on the red line by setting lambda H larger than 0. And then we will see wherever that ends up. For instance, if it ends up here, then the green constraint would be met. But if we end up here, then the green constraint wouldn't be met. Okay. And if, for instance, just take these away, let's say we would find a potential solution here where the green constraint is not met. What we then also have to do is we have to look at this one point, the only point where both constraint is met. Okay, so we'll see that. So let me take all of these away again, because we don't know where our potential solutions on these boundaries are. But this is what we're now going to do, is we're going to look on the boundaries where previously that was one step. This could now potentially be a 3-step procedure. So we're looking on boundaries. First, we are setting lambda G to larger than 0, but leaving lambda H equal to 0. Okay, we are looking on the green boundary. So if you do that, let's just quickly write down what let me do that in green so we know what boundary we are looking at. So we're getting from the first Lagrangian condition 1 over x1 minus 2 times lambda g, because that is now larger than 0. But we are still keeping lambda h equal to 0, so that term falls away, and that's equal to 0. From the second Lagrangian conditions, we're getting 1 over x2 minus 3 times lambda g. The lambda h we keep at 0 is equal to 0. So now we have two equations with three unknowns, x1, x2, and lambda g. So we need a third equation. Well, we invoke this complementary slackness condition, because if lambda g is larger than 0, then g has to be equal to 0. So we'll go to our g constraint, which is here, and we're using the 0 at the equal to 0 bit. So we're having 6 minus 2x1 minus 3x2 is equal to 0. Okay, so three equations, three unknowns. This can be solved. And I'm not gonna, because I want to concentrate on the big picture, I'm not gonna concentrate on the algebra here. I just tell you what the solution is. And of course, you at home can try and get this same solution given these three equations. We get to a point where x1 is equal to 3 over 2, x2 is equal to 1, and lambda g is equal to a third. So firstly, note that lambda g is larger than 0, which is great, because we also know, and we typically add that here, I forgot to add that here, we need that lambda g, of course, has to be larger or equal to 0, and lambda h, our Lagrangian multipliers, have to be larger or equal to 0. So it's larger or equal to 0, so that's fine. Okay, it's a potential solution, but what we haven't checked yet is whether this point is allowed by h, okay, by our second constraint. Now let's actually draw that point. Let's call it point A. Okay, let me do that in green. Let's actually draw that point on our little sketch, point A. So x1 is 3/2, that is 1.5, okay, and x2 is 1, so 3/2, 1. So it's around here. It's this point. This is point A. Now, if I drew correctly, you can already see that this point is outside of the red constraint, because the red constraint demands that values are inside this or below that red line. So let's confirm that. Let's go to the red constraint and plug in our x1, x2 values. So if we calculate, so g, our constraint here is 1 minus a sixth times x1, which is 3 over 2, minus x2. X2 is 1. So what do we have here? We have 1 minus that shorts to a quarter, minus 1. So 1 minus, so we certainly have something that is smaller than 0. So that means that is formal confirmation that this point A is not allowed by the red constraint. And we could see that graphically because that point is outside of the red constraint. Okay, that was a nice try, but that didn't give us a candidate solution. So what have we found out? That point A, it meets a number of the Lagrangian conditions, but it doesn't meet this one. Okay, this one was violated because here our constraint is smaller than 0. So let's try something else. Let's try where lambda h is larger than 0. So we are now looking on the red boundary, but we are setting lambda g equal to 0. So let's work that with red. So what we get is 1 over x1. So I'm going back to the Lagrangian condition, 1 over x1. That term will be 0 because I'm setting lambda g equal to 0, minus 1 over 6 lambda h is equal to 0. Then I'll go to the second one. I'll get 1 over x2 minus lambda h is equal to 0. So two equations with three unknowns, x1, x2, and lambda h. I need a third one. Now I'm looking at this complementary slackness condition, because if lambda h is larger than 0, then h has to be 0. So we're using the 0 bit here. The third equation is 1 minus 1 over 6 x1 minus x2 is equal to 0. So we're having three equations with three unknowns, x1, x2, and lambda h. Again, this can be solved. Again, I will not go through the algebra here. We'll call this point B. This will develop into point B. I'll give you the solutions. Again, you can yourself make sure that from these equations, you get to x1 being equal to 3, x2 being equal to a half, okay, and lambda g, lambda h being equal to 2. So again, that's larger than 0, that's great. So at this stage, that's still a candidate solution. So let's draw that on our line, x1, 3, x2, a half, so that point is around here. That is point B. Now, if I've drawn it correctly, then we can again see that point B isn't allowed by the green constraint. So again, that seems to suggest that this point isn't an actual potential solution, because it seems to be breaching this Lagrangian condition. But let's just make that formal and confirm that formally by plugging these coordinates for x1, x2 into our G constraint. So it's, that's the G constraint. I realized, okay, that's the G constraint. When I wrote here, when I evaluated point A, I should have evaluated here the H. I did evaluate the H constraint, but I called it the G constraint. Okay, so here was an H. So here's the G. So the G constraint is 6 minus 2 times x1. So x1 is 3, so minus 2 times 3. Minus 3 times x2, so minus 3 times x2. x2 is a half. So we get 6 minus 6 minus 3 halves. So it's minus 3 halves. That is smaller than 0. So that means this point B has been ruled out by the green constraint, as we predicted from looking at our little picture. Okay, so this means where are we now? We are in some sense, we're almost in a troublesome situation. We haven't, the unconstrained situation, we didn't find a potential solution. That's the part which I wiped away already. The constrained parts, we looked on the green line, didn't find a point which met all of the Lagrangian conditions. Then we looked on the red line, we didn't find a point that met all the Lagrangian conditions. So what can we do? Well, turns out there was actually one point we haven't looked at. And that point, which color am I going to use? Purple. Okay, that point is this point, the intersection. Let me call that point C, because at that point C, it's not only that lambda G is equal to 0, but also lambda H is equal to 0. Wrong what did I say? Both. So, I need the, sorry. Ooh, where's my rubber? Yeah. Sorry. It's lambda g is larger than 0 and lambda h is larger than 0. Because remember, on the boundary, we're looking at lambda h larger than 0 or lambda g larger than 0. But here, when we looked at these two cases, I always said either lambda h to be equal to 0 or lambda g to be equal to 0. So implicitly, I said, when we looked at this version here, I said, look at the green line, but not on that point C. And when we looked at this case, I basically said, look at the red line, but for the time being, not at point C, because I said lambda g equal to 0. So let's look for lambda g, the point where lambda g and lambda h is actually larger than 0. Just give myself a bit more space. So how are we going to do this? We are now basically ending up with, so I'll go back to our Lagrangian conditions, 1 over x1 minus 2 times lambda g minus a 6th lambda h is equal to 0. Go to the second one, 1 over x2 minus 3 lambda g minus lambda h is equal to 0. So 2 equations with 4 unknowns, x1, x2, lambda g, and lambda h. So I need 2 more equations. But now I can invoke both of my complementary slackness conditions. So I'm basically using both of my constraints. I know that I'm on both lines. So that is 6 minus 2x1 minus 3x2 is equal to 0. And 1 minus 1 over 6 x1 minus x2 is equal to 0. So now I have 4 equations in 4 unknowns. How we can potentially solve this. So I again spare ourselves in here the algebra. There's algebra in the solution document, which I will publish in the weekly schedule where I link the recording. I will publish the document. But perhaps in terms of strategy, there's a clever way to do this. If you look at these 2 equations, these are the 2 constraint equations. They don't involve the lambda g's and lambda h. It's just x1 and x2. It's 2 equations, 2 unknowns. You can solve that. And basically what you get from here, from these 2 equations, you get coordinates for x1 and x2, which are these coordinates for point C. Okay, and then once we know these coordinates, then we can figure out what lambda g and lambda h are to confirm that they are positive. So from here, so you can solve these 2, you will find out that x1 is equal to 2 and x2 is equal to 2/3. Okay, so that is 2, and I almost drew it nicely, and this is 2/3. Okay, so we already have x1 and x2. Now you can plug this x1, x2, you can plug that into here, which leaves you with these first 2 equations having only 2 unknowns, lambda g and lambda h. And I just tell you, and then you can solve that. What you will find is that lambda g is equal to 1 over 6, which is larger than 0, and lambda h is equal to 1, which is larger than 0. So that means, so this is point C, and at long last, we found a potential solution. Okay, we found a potential solution. It meets all the 6 Lagrangian conditions. All of these, 1 point that meets these. So we know that Lagrangian conditions are always necessary conditions. But sometimes they're also sufficient. When are Lagrangian conditions also sufficient? So that would mean, as long as the Lagrangian conditions are only necessary conditions, we know that the solution to the problem has to meet all of these conditions, but not every point that meets the conditions is necessarily the solution to the problem. So that's the stage at which we are at. We have 1 point, point C, which meets all of the conditions. So if there's a solution, since there's only 1 point, if there's a solution, it has to be that point. But we don't know yet whether it is the solution. Now, there are, of course, situations where the Lagrangian conditions are also necessary conditions, also sufficient conditions, which would mean that given we found that point, we would also know that it is the solution. Under what scenario are the Lagrangian conditions also necessary conditions? And that scenario is if the function itself is globally concave, and the constraints, usually we're only talking about one constraint, but now it's constraints, are also globally concave. If that both of that is true, then the Lagrangian conditions L dot C are necessary and sufficient. So let's look at the constraints. Look at these constraints. Both constraints, actually. Yes.
I just want to stop you before going further. There are some confusion that why do we need to solve in this kind of setting the constraints like lambda g and lambda h greater than or equal to 0 instead of just for clarification, their question is they know the intersection point of the two constraint already. So if they equate the two constraint to find out the intersection point, or why we are going through this procedure instead of that.
So is the question why do we need to find out these values, or why do we need to look at points?
Yes, to find point C solutions,
yes.
Why are we not just equating the two constants because they're the intersection point of the two?
That's right. That's exactly what is done here. So that's a good point. This is when we wrote down what we get from the Lagrangian conditions. The last two are just the constraints. Okay. Yeah. And if you set these two equal, you get these two coordinates. Okay, you get that coordinate. I wonder whether the question is, why do we bother about first finding point A and then finding point B? Why don't we immediately go to point C? Is that the question?
I feel like that, yeah.
Okay, so it's a super good question. Let's imagine that, let me just make this a little bit bigger for this discussion. Let's imagine that when we looked on the red boundary, we would have found this point D. Okay, that and with a different slope of the function, that could have been possible. Okay, now if we had found point D, then we know the best possible point on that line would have been point D. Okay, in that case, we wouldn't have had to look at point C anymore. Then we would know that D is our point. We only had to look at point C because what we actually found was point B, but that wasn't allowed by the green constraint. Okay, point D, however, that would have been allowed by the green constraint. And then we would have found that the solution to the problem would have been point D. So we only need to go to that third point here if on if we don't find an individual, looking on individual constraints, if we don't find an allowed potential solution. Okay.
Just a quick question. Are they not both potential solutions, D and C?
So D and C, so, okay, so the question would be, would in that case, would we also find C to be a potential solution? Yes, but we would find the function value at point D to be larger than the function value at point C. Yeah. Okay, that's not immediately obvious. You sort of have to trust me on that. You can, in a particular example, you could, of course, test it.
Yes.
Okay, so let me take this away. Oh, okay, I've exhausted my turn. So point D doesn't.
Another question. Is this kind of problem going to appear in exam with 2 lambdas?
Everything is examinable, but for linear difference equations. So I'm not, you can ask me all day long, is that type of problem going to be on the exam? I will always say everything is examinable. Okay. So where were we? Okay. So we were at that point where I wanted to see whether our Lagrangian conditions are also sufficient. So we were looking at the constraints. Are they concave? And the answer is yes. Both constraints are linear constraints, and we know linear constraints are both concave and convex globally. So yes, they are concave. What about the function? Is that globally concave? Now, if you look at that function, it's a logarithmic function. If you can sort of picture that function, you possibly immediately realize it is concave, but you could calculate the Hessian for that function. So the Hessian for that function, x1, x2, is, I'll just put it down, and you could confirm that this is correct, is negative 1 over x1 squared, negative 1 over x2 squared. You can see that from the example 4, constraint optimization example 4, because the same here. So that's the Hessian. The question is the Hessian here x1, x2 negative semi-definite for all x1 and x2 in our domain? Okay, so that's for all positive x1 and x2. And the answer to that question is yes, because you can see here you have x1 squared, that's always positive. So if you have some negative times something positive, that's always negative. That diagonal is always going to be negative. So the determinant can never be negative, because that's negative, that times that will be positive. When you calculate the determinant of H is going to be negative 1 over x1 squared times negative 1 over x2 squared minus 0. So that is always going to be positive. So yes, the function, so we said the constraints are globally concave, the function is globally concave. That means that in our case, the Lagrangian conditions are necessary and sufficient. And that means, ta-da, our point C is indeed the solution to the problem. I chose to talk through this problem here because by going slightly outside our established and recipe so far, with one constraint, we hopefully had to sort of push a little bit at the boundaries of the Lagrangian method, and we could do that if we really understand what the Lagrangian method does. Okay, and it's about splitting up this sort of area in our domain into sub-areas and looking in the different sub-areas for potential solutions, but then testing whether that really is a potential solution. And that's what we've done here. Okay, we first looked in the unconstrained area, tested against the constraints. Actually, we didn't find a potential solution in the unconstrained area at all. And then we divided our boundary here up into the 3 different parts. Okay. So, Banali, any more question you?
There is a question, what would you do if either the function or the constraints are not globally concave?
Oh, excellent question. So then you need to understand whether the function, how it behaves everywhere. Now here in this particular case, what you can see here is that the area in which we are actually looking is really a confined area. Okay, it's this, was this green, green shaded area here. So here we actually don't need to look at, how does the function behave if, say, x1 goes to infinity. Because there isn't, x1 isn't allowed to go to infinity, or x2 isn't allowed to infinity. And in fact, so some of you may perhaps realize that it turns out that this constraint is actually a bounded constraint. Okay, it's not a compact one because x1 and x2 is not allowed to be 0. So that boundary here at the bottom isn't part of the allowed area. So it's bounded. So we have a very restricted area. And if you have this, you will find the solution through your method here. Okay, so, but of course you could have multiple constraints and the remaining area would still leave you with some, with x2 or x1 being allowed to go to infinity.